Alright, let's get started. So, next section, what are we, 5.2? 6.2. Or 6.2? Let me get my book set up. 6.2 to make sure we don't skip anything. I have up to the theorem, so right there. Okay, so section 6.2 is all about the Archimedean-Riemann theorem, or the Archimedes-Riemann theorem, which is going to be this theorem right here. Ultimately, it's going to be a theorem that tells us when we can integrate different types of functions, or when functions are integrable. You'll remember last week we talked about this, even though after the class was over, we started by talking about what the definition of an integral was, and then we went all the way to actually calculating a specific integral. That's exactly what we're going to do again today, just more detail now. But we'll end with calculating an integral, and we'll start with the definition of what an integral is. So, or when something is integrable, and yeah, what the integral is. So let's do it. Quick recap, remember what this symbol was? This is going to be the integral, right? This is the integral of f from a to b. And it's understood when you see this that f is a function defined from a to b to r. Okay, so let f be a function from ab to r, and let it be bounded, so we're not taking off to infinity, because remember intuitively, the integral is going to give us the area. If the function takes off to infinity, how do you get an area under infinity? It becomes a mess. So let f be a function and let it be bounded. Then f is integrable, provided that the lower Darboux sum and the the lower integral and the upper integral are equal. If you remember that we had our inequality that, intuitively speaking, the lower integral is always less than or equal to the actual integral, is always less than or equal to the upper integral. That was our intuition for how we define these things. Because this is as good approximation as your lower Darboux sums get, this is as good approximation as your upper Darboux sums get, and this is sandwiched between them. So if this is equal to this, then it's also going to be equal to this. That's the intuition there. So we're saying that a function has an integral if the lower Darboux sum and the upper Darboux sum are equal. If they're equal, then it's integrable, and we define its integral to be those values. Doesn't matter which one since they're equal. Make sense? And hopefully intuitive sense. So reminder, last week we proved this line here. Just look out for a second, make sure it makes sense. The lower Darboux sum is less than or equal to the lower integral, is less than or equal to the upper integral, is less than or equal to any upper Darboux sum. And we don't even have to use the same partition here. Those can be separate partitions, doesn't matter. This is still always the case. You remember going over this? Okay, so I'm just going to write this inequality. I'm going to write information from this inequality in 3 different ways that turns out are going to be useful to reference. So let's make sure each of these inequalities make sense. First off, since this number is bigger than this number, or they're the same, when I take their difference, I get something greater than or equal to 0. That's our definition of inequalities. If you remember way back to the beginning, we say that A is less than B is logically equivalent to B minus A is greater than 0. So equals like that. Way back to the beginning of the class. So anyways, and it should make intuitive sense, right? Since 6 is bigger than 4, 6 minus 4 is greater than 0. So since that is bigger than that, this difference has to be greater than or equal to 0. Now notice in going from this inequality to this inequality, all I did was make this number even bigger and this number even smaller potentially. They could have stayed the same, but all I could have done was made this number bigger, and all I could have done was made this number smaller. So that gives me an even bigger difference, which gives me a bigger number. You good with that inequality? This is the one we'll reference most of the time. These ones just give us some somewhat useful information, but this is one we'll use over and over again to make sure this makes perfect sense. Because what we're going to be doing over and over again to show that these two things are equal is I'm going to show that the limit of these two things goes to 0, and therefore the difference between these two things goes to 0. That's what we're ultimately going to be doing. So that's why this one's so useful. Now, two more that are kind of useful, we'll only reference them once, but let's just make sure they make sense. Here, I'm saying this, the upper Darboux sum, minus the upper integral, that difference is still greater than or equal to 0, right? And it's also less than or equal to this thing. Obviously, the difference between those two things is going to be greater than or equal to the difference between those two things. Double quotation means just write that same thing again. With me? Is that one weird?
I feel like you worded it different.
The difference between these two
Is greater than or equal to?
Oh, it's less than or equal to, sorry.
All right.
Thank you. Is less than or equal to the difference between these two.
Okay, that makes sense.
Yeah, thank you. Said that wrong, but the way I wrote it right. Similarly, the difference between these two is less than or equal to the difference between these two. That's what we're saying here. Why are we doing that? All we're going to say with these two is, look, if the limit of these two difference goes to 0, then it turns out that in the limit of our upper Darboux sums is going to be the upper integral, and the limit of our lower Darboux sums is going to be the lower integral. So that's what those two inequalities are going to give us. Anyways, so now let's get to the heart of this whole section, proving the Archimedean-Riemann theorem. So let f from a be to r be bounded. Then f is integrable. In other words, its upper and lower Darboux sums are equal. Its upper and lower Darboux sums, sorry. Its upper and lower integral are equal. That's what it means for it to be integrable, right? If and only if there exists a sequence of partitions, call it Pn. Remember what a partition is? Okay, so some sequence of partitions that are going to make all our intervals get smaller and smaller and smaller, such that the limit as n goes to infinity of the difference between our upper and lower Darboux sum goes to 0. Does that make sense what one of those sequence of partitions might look like? Let's look at one real quick. So really try and make sure we see exactly what's going on. So I've got some function defined from A to B, right? And I give it some partition, something like that. So our lower Darboux sum is going to go like that, and our upper Darboux sum would come all the way up to here on that triangle, or rectangle. Similarly, our lower Darboux sum here would come up like that, and our upper, sorry, keep that dotted so we can distinguish the difference. And our upper would have come all the way up to here. Here, our lower would have been something like that. Our upper would have come all the way up to here. And then here, our lower, something like that. And our upper would have come all the way up to, need the function to be drawn further, all the way up to here. Something like that. Right? So now what we're saying is, this thing is going to be integrable. It's, remember that my lower integral, intuitively speaking, well, let's just say it exactly what it is. What is my lower integral defined to be? The supremum of my lower Darboux sums. So this was one partition. I could have come up with a better partition that gave me a better approximation with my lower Darboux sum, right? If I would have added way more points in here, that would have been a much better approximation. And so I would have gotten closer to the actual integral, the actual area. This is the supremum. It's the least upper bound of every possible lower Darboux sum I can make. Right? So what we're saying is, this function right here is going to be integrable if it's possible for me to find a sequence of partitions. So some sequence of partitions, here's one partition, and then I could go through and divide all these in half. Okay, there's another partition, and then I could go through and divide all those in half. There's another partition, I can keep doing that, and make a sequence of partitions. what's going to happen in that sequence of partitions? All these are going to get infinitely small. All these little intervals are going to get infinitely small, right? In the limit. And we're going to calculate perfectly the area under the seam. So the difference between what my lower Darboux sums and what my upper Darboux sums give me is going to get, they're both going to get closer and closer to giving me the exact area, and so their difference is going to get closer and closer to 0. So in the limit, the difference between my upper and lower Darboux sums is going to be 0. They're going to give me the exact same number in the limit. If that's the case, then this thing's going to be integrable. The lower integral is going to equal the upper integral. It's going to turn out that the least upper bound of all my lower Darboux sums and the greatest lower bound of all my upper Darboux sums are going to be the exact same thing. Does that make sense? That's intuitively what this says. Now let's actually prove it. Furthermore, if it is the case, then the limit of our lower Darboux sums gives me the lower integral, and the limit of our upper Darboux sums gives me the upper integral. So showing this at the end is trivial, but we'll show that. This is the heart of it, up to this point right here, up to this period. So we'll focus on that, and then we'll show this afterthought, because it's real easy. So let's jump into the actual proof. Let's see, which way do we want to prove first? I'm not going to write the top part. I'm just going to go straight to 1. And we're going to be proving it. We'll prove this way first, whichever way that is. So we'll prove this way. So I'm going, let's see. So let f, so I already have my f defined. F is an unbounded, or is a bounded function defined on the closed interval a, b to r. So we already have f defined. So now I'm proving this way. So we're going to say assume f is integrable. Assume f is integrable, which is the exact same thing as what? That means that the lower integral is equal to the upper integral is equal to the actual integral. Right? That's the definition of a function being integrable.
And over here you had 2 dots by your equal sign. I'm just wondering what the difference is.
Oh, this just means we're defining the symbol now. We're defining this to be that. It's just specifying, what's it called, the definiendum from the definiens. So you know we are defining this, a symbol that we don't know, in terms of symbols that we do know. And it's just making that explicit. Still just an equal sign.
All right.
It's just calling attention to, hey, this is a symbol that's yet to be defined. We now have it defined. The author uses 3 lines. So authors go back and forth between their notation. I use this notation simply because in my education, it's the first one I came across, so it's one that sticks with me. But that's the way the author does it. Probably should have had that conversation a while ago. Because if you've been reading your book, probably been confused by those 3 lines all over the place. Anyways, okay, so assume f is integrable. Now what are we trying to show? We're trying to show that there exists some sequence of partitions that makes this statement true. I now need to find a sequence of partitions such that the limit as n goes to infinity of the upper Darboux sum on that sequence minus the lower Darboux sum on that sequence gives me 0. Understand what we're trying to do now? Okay, so 2. So let n be any natural number, comma, and observe that there must exist some partition P prime such that, let's see, on my lower Darboux sum such that 1 minus n, let's start by drawing the lower Darboux sum, sorry, give me a second to make sure I got my thinking right. The idea will be pretty straightforward, but let's see, this was the supremum, this was the least upper bound, so this isn't an upper bound, so it's less than the lower Darboux sum. Okay, now explain. Okay, so pick some natural number n. Now remember, by definition, what is this? This is the supremum. This is the least upper bound of all lower Darboux sums. It's the least upper bound of all lower Darboux sums. It is impossible for me to come up with a lower Darboux sum bigger than this because this is an upper bound. Furthermore, it's the least upper bound, meaning any number smaller than this is not an upper bound for all lower Darboux sums. So this minus 1 over n is not an upper bound for all lower Darboux sums, which means that there is some partition out there such that that lower Darboux sum gives me a number bigger than this. Does all the logic there make sense? Wonderful. So and observe that there exists p prime such that that is true, and there exists, we'll call it p double prime, such that the upper integral on f p double prime, this is going to be the exact same thinking, is less than the upper integral of f plus 1 over n. So remember what this symbol is now. How do we define this symbol? This is the infimum of all upper Darboux sums. This is the greatest lower bound of all upper Darboux sums. This is less than any possible upper Darboux sum you can come up with. But it's the smallest thing that's less than any upper Darboux sum you can come up with. So when I plus a little bit to it, it is no longer the least upper bound. So this is no longer the least upper bound, the greatest lower bound. Sorry, infimum, greatest lower bound. Greatest lower bound. So this is the greatest lower bound. When you add a little bit to it, then it's no longer a lower bound, which means that there is some upper Darboux sum less than it. The logic there is pretty straightforward with lower and upper Darboux sums, or infimums and supremums. We've used infimums and supremums a lot. I just keep saying my words wrong. But everything I have written on the board is 100% right. I just keep saying things wrong. Does what I have written on the board make sense? Yeah. Okay, so now we're going to take a refinement of this thing, and both these inequalities are going to be true. Notice, if I take a refinement, if I take a better approximation for my lower Darboux sums, it can only make the number bigger. Right? A lower Darboux sum gives me something less than the integral. If I take a refinement of its partition, I could have only made it a better approximation, made the lower Darboux sum's number bigger. So when I do the refinement between these two partitions, when I union those partitions together basically, take a common refinement, I could have only made this number bigger, so this inequality is still going to be true, and I could have only made this number smaller, so this inequality is still going to be true. So that's what I'm going to do. Let Pn be a common refinement, I guess we'll say. I won't call it union in case that gets confusing. Be a common refinement of P prime and P double prime, which gives us that. And I'm also going to do a substitution here, so be ready for this to all come together. The integral from AB to F minus 1 over n is less than the lower Darboux sum on F with the partition Pn, and the upper Darboux sum on F with Pn is going to be less than the integral from A to B of F. So I plugged in my refinements, and notice since we know that this thing's integrable, we can replace our lower integral with just the integral and our upper integral with just the integral. So 2 substitutions there. Same exact equations that we have written up here. All I did was replace that and that with just the integral sign, and I replaced my p prime and my p double prime with pn.
Is there a reason you got rid of plus 1 over n?
No, there is not a reason I got rid of that. Thank you. Okay, this should be the exact same equations with just some substitutions. Do I have it right? Okay, so now what we're trying to show is that this is the case. The limit as n goes to infinity of this difference is 0. So let's set up this difference now. So observe that our upper Darboux sum, Fpn, minus our lower Darboux sum, Fpn, is going to be less than a bigger number minus an even smaller number. So this number is bigger than this number, and this number is less than this number. Maybe I should have written it first and then specified there. The integral from a, b, f plus 1 over n minus, and maybe put parentheses here to make it very explicit. So this number we know is bigger than this number, and this number we know is smaller than this number. So this difference is a bigger difference than this difference. Just using the inequalities we have above it. Does that make sense? Maybe right is equal to, so you can see exactly where this is going. That is equal to 2 over n. Because look at this integral cancels out with that integral. We have positive 1 over n minus negative 1 over n gives us 2 over n. Now take our limit. The limit as n goes to infinity of Yep. And when you take the limit of both sides, all it can do is switch the less than an inequality to, what do they call it when you put the equals in there as well? An inequality with the equals in there.
Less than or equal to?
Yeah. So in taking the limit of both sides of this, all we could have done is turn that from a less than to a less than or equal to. But everything else is the same. Right? And we know how to take that limit. That's just 0. I don't think I need to prove that the limit of 2 over n is 0. I think you're far enough along you can just see that. So there we go. So we got the limit of this difference is less than or equal to 0. Or in other words, since this is always a positive number, it's going to be equal to 0. But I think we are just showing equal to 0. Yeah, we got it's less than or equal to this is equal to 0. So this is always a positive number, so it can only be equal to 0. Make sense? So that's our sequence. So we found a sequence of partitions that made so that this was true. Any questions there? This is the hard part. Going the other way is a lot easier. Alright, so let's do it the other way now. Let's see. So the other way, we say, now we get to assume that we have some sequence of partitions. So now we say, let Pn be a sequence of partitions such that the limit as n goes to infinity of the upper Darboux sum minus the lower Darboux sum is equal to 0. Right? Assume we have the partitions. All we're going to do is use this inequality. This one. So, I don't even know if you want me to finish writing it. You can say if you want me to finish writing it, but I'll just explain first and then I think you'll get it. So, then we say, observe that we have this inequality, then take the limit of this inequality as n goes to infinity. We get that goes to 0, so we get that is equal to that. You want to see it, or do you think you understand from just me saying it? We can write it out. Write it? Write it? Okay. So, I'm going to just call this equation 1. Since equation 1, then we're doing this one. 0 is less than or equal to the lower integral minus the upper integral. Or sorry, the upper minus the lower. Yeah, I have it written right over there. I just read it wrong. The upper minus the lower integral, which is going to be less than or equal to the limit as n goes to infinity of the upper Darboux sum minus the lower Darboux sum, which is equal to 0. So now I have this thing is between 0 and 0, so this thing equals 0. So that gives me that my upper minus my lower is 0. That gives me my upper integral minus my lower integral equals 0, which gives me then, transpose that to the other side of the equation, which gives me that my upper integral is equal to my lower integral, which then we say is equal to the integral. Now notice, maybe it's worth pointing out, this proof does not tell us anything about what the integral is. It was just saying whether or not we could calculate the integral of something. So we're just proving that, okay, functions like this we could calculate the integral of. Tells us nothing about how to actually go about calculating it. Important point to keep in mind.
Just to clarify, in statement 1, I guess, you took the limit of all three, I guess, sides of the inequality, but the two on the left.
If this is always true, then when we take the limit over here, we just have to switch that to an inequality, and it's still going to be true. If this is true for every value, p that I plug in, then it's going to be true. That might have been a greater than. Let's say that that was just a greater than. Then in taking the limit here, that only adds the equal sign there. Because like in the limit, you could have only added just one more point beyond what you did. So no, we don't need to take the limit of all three of these. We could as n goes to infinity. You could think about it that way, but that's just a constant, that's just a constant, that's just a constant, and then this comes out.
Right.
So yeah, you can think about it that way if you want. It doesn't change anything. Any other questions? Okay, so that's the proof of the theorem. Oh, and then we said in such cases, the limit as n goes to infinity of the lower integral of the lower Darboux sum is going to be the lower integral, and limit as n goes to infinity of the upper Darboux sum is going to be the upper integral. And that just comes from these inequalities. Same logic we used here. Since this goes to 0, then this is equal to this. Since this goes to 0, then this is equal to this in the limit. Make sense? I don't think you need to write that out. You can just see it. And so now this gives us a way to actually calculate the integral now. So if I were to take the limit, if I know that something's integrable, there's two steps here. You can't just go calculating an integral. You have to make sure first that it is integrable. And then if it is integrable, we have a way of checking that. Now we have a way of calculating the integral. If I take this limit, that will give me the lower integral, which is the integral. So I can calculate the limit this way, or I can calculate the limit this way. So now we have two ways of actually calculating the limit. And you'll notice last week at the end of class, this is exactly what I did. I calculated the limit of the upper Darboux sums with a partition that did this. And we just used a regular partition. Oh, terminology. a sequence of partitions that makes this difference go to 0, we call an Archimedean sequence of partitions. Archimedean sequence of partitions is a sequence of partitions that makes the Archimedean-Riemann theorem true. So another way that we can state the theorem now is that a function like this is integrable if and only if there exists an Archimedean sequence of partitions. Make sense? Good? Okay. So now, I think we're just going to prove that increasing functions are, oh, maybe we have to talk about the gap in a regular partition first. Now we'll see. All right. So, next definition, I think, is just a gap, or is a regular partition? Regular partition is our next definition. Okay, a regular partition, I don't want you to get confused by the math of it because it's a very simple concept. If I have some interval, a to b, and it's defined on the real number line, but I have some interval a to b on the real number line. A regular partition is a partition that divides it up into even parts. So pick some number n, like 5, and divide it up into 5 even parts. That's all a regular partition is. Now, the points in the partition, x of I, the ith point in the partition, if you create an m partition on that thing. So I divide this thing up into n pieces. So this is x of 0, x of 1, not x of 1, or x of I. X of 0 is this one, x of 1 is this one, x of I somewhere in the middle. It's just the ith one. And then the very last one is going to be x of n. Okay, so I'm dividing the partition up into n pieces. Where is the position of the ith x coordinate in that partition? You get that from just a plus I times b minus a over n. So let's make sure that this makes perfect sense, and you could have come up with this equation yourself if you would have thought about it, I'm sure. What is the distance of one of these intervals if this is regular partition? We divide this whole, what's the length of this whole thing?
B minus a.
B minus a, right? So what is the length of one of these intervals?
N. No.
B minus a divided by n,
Yeah.
right? If this whole distance is b minus a, and I've divided this up into n pieces, then each of these little pieces is just b minus a over n. So my first partition point, x of 0, is just going to be at a, right? Which is the same thing as when I start at a, and then I add 0 of these intervals. My x of 1 is going to start at a, but then it's going to be what you get when you add 1 of those intervals. Dot, 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 dot. My nth one, which we know is at b, is going to be what you get if you start at a, and then you add n of these intervals. N's go out, so that's a plus b minus a, which is equal to b, just as expected. So x of I is equal to this, where 0 less than or equal to I less than or equal to n, for all I between 0 and n. Obviously is defined outside of that. That's what a regular partition is. Pretty straightforward. Okay, useful equation to even just memorize. But I'm almost positive you could have derived this equation yourself. Very straightforward. The reason I'm stressing this so much is because we're going to be using this when we calculate integrals by hand. This is what I did last week to calculate where all the points were that I was going to get the height of.
So, in the theorem we just proved, we have to have a sequence of partitions that it does not have to be regular partitions? Can they be?
No, it just has to be a sequence of partitions where the length of the intervals goes to 0. So notice, I'll give you one real quick, just so that you can see one. So imagine I start out with A, B, and I start out with a partition like this. Good? Now here's how I create my sequence from here. I keep dividing all those in half. So I divide this one in half, I divide this one in half, I divide this one in half, I divide this one in half. It's not regular. And then I could keep making my sequence divide all those in half. So I divide this in half, 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 divide this in half. Notice the length of all my the length of the intervals are always going to go to 0 in this case, but that is not a regular partition. Those lengths are all over the place. So all we care about is that we have a special name for the largest interval. We call it the gap of the partition. So if the gap of the partition goes to 0, if the length of your biggest interval goes to 0, then it satisfies this. When we calculate by hand, we obviously just use regular partitions because for obvious reasons they're the easiest to work with. But you don't have to use regular partitions. So since we already said it, let's just write out exactly what the definition is. The gap of a partition P, its definition is, maybe I want to keep it up here, so maybe I'll put it, why do I keep grabbing this one? Put it further away so I don't actually use it. Okay, so we talked about a regular partition. With regular partition, and the point x of I is equal to a plus I times b minus a over n. Let's keep that up there for reference. And now, the gap of a partition, not cap, the gap of a partition P is defined to be the max of, how did I want to write this? I don't know if I really like that. We'll do it this way. The max of x of I minus x of I minus 1, the max interval for, let's see, we can't have I equal to 0 in that case, it has to start at 1. So 1 less than or equal to I less than or equal to n. The gap is your largest interval. That's all it is. It's not the largest length of your interval, it's actually the interval. So it's not a number, it's an interval. It's the largest interval. So that is still a closed interval, and it's the largest of those. Assuming that we have some way of talking about the largest, which would be the absolute value of their difference. Okay. So that's the gap. Now I think we're ready to show that all monotonically increasing functions are integrable when defined on a closed interval a to b. Okay, so proof, this is just an example problem, but it's one that's worth doing. Proof, if f from a, b to r is monotonically increasing, then f is integrable. We remember what it means for it to be monotonically increasing? I don't know if we're doing monotonically increasing or strictly increasing. Monotonically increasing. Okay. So we're right. Okay, so I'm trying to prove that any monotonically increasing function you define on the closed interval AB is going to be integrable. Now notice we already know that this thing's bounded, right? Because f of b is its upper bound, and that has to be defined. Otherwise this wouldn't be a function. So we already know it's bounded. Okay. So now, So we're showing that this thing is integrable. How are we going to do it? We're going to show that this limit, that this difference here goes to 0 when we use a regular partition. So I'm going to put a regular partition on that thing, which is going to be one of these Archimedean partitions, and show that the limit of it, this difference between its upper and lower Darboux sums in the limit is 0. Therefore, it's integrable. We're not proving what the integral is, we're just proving that we can calculate an integral of all functions that look like this now. That's all we're proving. And then we'll actually calculate some by hand afterwards. Make sense? Okay. So, 1. Let f from a, b to r be monotonically increasing, comma, and note that f is bounded. It's bounded from above by f of b, and it's bounded from below by f of a. Okay. 2. Let P of n be a sequence of regular partitions. So p sub 1 divides it up into 1 intervals, p sub 2 divides up into 2 even intervals, p sub 10 divides up into 10 even intervals, etc. Understand what our sequence of partitions is? Okay, so now let's just, maybe let's look at the difference in general, and then we'll look at the difference when we take the limit. Observe that our upper Darboux sum for any partition we pick out of the sequence minus our lower Darboux sum is equal to the sum from I equals 1 to n of, overthinking it, let's not get actual numbers here. The upper Darboux sum is big M sub I times, since it's a regular partition, maybe I'll write it out here and then we'll erase it and redraw it. Times x sub I minus x sub I minus 1. I just realized on the gap, I wrote a difference in there, not an interval. Now I'm wondering if the gap is a number. So I thought it was the interval. The gap is a number. Okay, I lied to you when I said the gap is an interval. It's not, it's a number. Which is why I wrote it that way. Sorry. So the gap is the size of the largest interval. It's not the largest interval, it's the length of the largest interval. Okay. Anyways, back here. So notice, well, no, we'll just plug in for this later. But my upper Darboux sum by definition is this, right? It's the highest point we reach in an interval times the length of the interval. And we keep doing that for every interval. That's how you calculate the area of one of the rectangles. The area of one of the rectangles is the highest point the function reaches on that interval times the width of that interval. The height times the width gives you the whole area of the rectangle. You with me? Now, since this thing is a regular partition, then all our interval lengths are the exact same number. And what is that number?
B minus A.
It's just b minus a over n. So don't get confused when I replace this with this. Does that make perfect sense? Okay, let's draw a picture real quick. Here's A, here's B, and I've got some function like that. we're doing, in this case, it's upper Darboux sums. So I create some partition. Now it's a regular partition, so I have to divide this thing up into even pieces. Pick some n, doesn't matter what your n is. So here's a case for n equal to 4. I tried to divide this up into 4 equal pieces. With me? When we look at the upper Darboux sum on this thing, our rectangles are going to look something like this.
That's our function.
So this right here is big M sub 4. This right here is big M sub 3. This right here is big M sub 2. This right here is big M sub 1. Right? What is the length of one of these intervals?
It's a plus I times b times a minus I.
It's this whole distance, which is b minus a, divided by 4. It's 1/4 of the whole distance. That's what it is.
Okay.
Or in general, it's 1/n of the whole distance. In this case, n is 4. So each one of these rectangles, the base width of the rectangle is b minus a over n. Does that make sense? Okay. So they all have the same base width. So when I'm adding up all these rectangles, so that's the sum from I equals 1 to 4 in this special case, when n is 4. And then we're doing m sub 1 times this distance, plus m sub 2, when you plug 2 into this equation, times that distance, which is the same as that distance, etc. M sub 3, m sub 4, and we're done. So you okay with this substitution for this now, when we have a regular partition? And now we're going to do the same thing with the lower Darboux sum. So this is minus. Now notice the sum ends, the sum of these things, now minus the sum from I equals 1 to n of little m sub I times b minus a over n. Exact same thinking. Good? So now I have a constant times this term that we keep adding up. So I can factor this out of my sum. Similarly, I can factor this out of my sum. Maybe we'll do it in 2 steps, and I won't factor it out the difference yet. But so this gives me, so this is equal to, this difference is equal to this difference is equal to, I'm going to factor this constant out of each of those sums. So we get b minus a over n times the sum from m, not m, from I equal 1 to n of big M sub I minus, once again, b minus a over n times the sum from I equals 1 to n of little m sub I. Good? Now, we have a constant times something, and we have that same constant times something, and we're taking their difference. So now I can factor clear out the difference. So this is equal to b minus a over n times the difference of the sums. The sum from I equals 1 to n of big M sub I minus the sum from I equals 1 to n of little m sub I. Good with the algebra up to there? Any weird step in there that you don't like? Okay, so now remember what our function is. This picture's a little misleading because we know that our function is monotonically increasing. And this one, we have it going down part of the way. So let me redraw one really quick that's monotonically increasing. So a monotonically increasing function might look can't add the code down at all, so that's just something like that. So erase some of that, so we have some room to draw. Here's A, here's B, so we have the function defined on that interval. We have some partition of it. We'll divide it up into 4 even pieces again. I'll do my lower Darboux sum in dotted lines. And then I'll add on the upper Darboux sum, solid lines from there. Good? So now, notice what we have is we have this distance times the difference of the height on each of the intervals. So when I is equal to 1, we're talking about this difference. We're talking about big M sub 1 minus little m sub 1. And here we're talking about big M sub 2 minus little m sub 2. Here we're talking about big M sub 3 minus little m sub 3. Here we're talking about big M sub 4 minus little m sub 4. So when I is equal to 1, we're adding up, if I color that in, well, you get these up to pink. We're adding up this, the difference here. When it's 2, we're adding up this. When it's 3, we're adding up this. And when it's 4, we're adding up this. So we're doing the height of this box times this distance, plus the height of this box times this distance, plus the height of this box times this distance, plus the height of this box times this distance. Which notice if I were to take all those boxes now and stack them on top of each other, then we'd be left with one big box that started down here and went up like this, but this distance is still the same as that, is the same as that, is the same as that, is the same as that. So I could stack all those pink boxes on top of each other to get one big pink box. You see how we do that?
I'm missing the point.
Well, now, this is, what's the base of this box? B minus A over N. And what's the height of the box? The point is, we know the height of that thing.
F of B minus F of A.
Wonderful! This point right here has height FB. This point right here has height FA. So now the height of that box is F of B minus F of A. The point of all that is that we know what this difference evaluates to.
Oh.
This is equal to F of B minus F of A. You with me? Now, that's not how I'm going to evaluate this. I want to show you that intuitively. Actually, no, it is. I don't want to have to plug in the points. So, actually, maybe it is worth doing. So we'll do it here. Because I want you to also see how it pops out in the math as well. So, if we were to expand this thing out, what would it look like? So let's expand it. Maybe I'll just write it here. So we know that this is going to come out to F of B minus F of A. But I want to make sure you can see it in the math, and then I'll just erase what I draw here. So when we expand this sum out, what is it? That's going to be n sub 1 plus m sub 2 plus dot 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 plus the very last term in the sequence is going to be f of b. Oops, little b. So we start out at that point, then that point, then that point. Our very last one is always just going to be f of b. You with me? Now we're subtracting this sequence away. The first term in this sequence, so that's our sum, and then we're going to minus from it. The first term in this sequence, in this sequence, is f of little a, right? Our first smallest point is f of a, minus. Now, little m sub 2, our lowest point for this rectangle is our highest point for the previous rectangle. So little m sub 2 is equal to big M sub 1. Little m sub 3 is equal to big M sub 2, etc. So I should have written one more term in this sequence, so let me expand this sequence out a little bit more to really drive the point home. This is plus big M of n minus 1, the second to last one. And then our last one, big M sub n, is the same thing as f of b. Okay, here we're going to get minus f of a, but now plus big M sub 1, not I, plus big M sub 2, plus in the last term of this sequence is going to be big M sub n minus 1. So when I do this minus this, all those n's are going to cancel out, leaving me with f of b minus f of a. Make sense? Exact same thing that we talked about intuitively up here. It's just wanted you to make sure we don't have to rely on a picture to put this proof together. Okay. And notice that the reason that this is true and this is true is because we know that the function is monotonically increasing. That's only true since we know that the function is monotonically increasing. This is not true in general. If that function was going up and down, this is definitely not the case. So very special function, which is what's helping us do this calculation. Okay. Oh, I forgot to put my b minus a here, sorry. We know this difference is f of b minus f of a, but we still have it multiplied by this. So I have b minus a over n times f of b minus f of a, which you'll notice is the exact same thing as the area of that big rectangle there. That is the difference between the upper and lower Darboux sum. With me? Now don't lose track of what we're trying to prove. We're trying to prove that the limit as n goes to infinity of their difference is 0. So now we need to take the limit as n goes to infinity of the sink, which is going to be 0. Because you have a constant minus constant, that's just a number, times a number, divided by n as n goes to infinity. So this is, maybe write this thing one more way before we take our limit to make it very clear that this is definitely going to go to 0. That's b minus a, which is just a number, times f of b minus f of a, which is just a number, all divided by n. So for then the limit as n goes to infinity of the upper Darboux sum minus the lower Darboux sum is equal to the limit as n goes to infinity of this sink of b minus a times f of b minus f of a all over n, which is equal to 0. And we're done. So what did we just prove? We proved that if you have a monotonically increasing function, defined on some closed bounded interval, then it has an integral, and you should be able to get its integral. Well, it does have an integral. That's what we should say. It does have an integral. You won't always be able to find its integral, but it does have an integral. And for some of them, any function now that we come across that we know is of this form, we at least know it is integrable, and so we stand a chance to find out what its integral is. Okay. So now I think we're ready to do an example. He also proves that all step functions are integrable. I don't want to go through that proof because you don't come across step functions that often. You can read over it, it's not that crazy of an idea. But step functions are functions that look like this. And maybe we don't include there, but then it looks like this. And they just have different steps as they go along. And obviously, to calculate its integral, you just calculate the area under each of these. So we know those are integrable. We know calculating their integral is pretty straightforward.
So a function doesn't
You
have
can-
to be continuous to be integrable.
Correct. It just has to satisfy that condition. So you can read through the example that he has there on how he explains this. It just feels like a lot of explanation for not very much payoff. Because it's already pretty intuitive to us that that would be the case. Anyways, so now let's, he introduces Leibniz notation, and then he goes on to calculate some by hand. So Leibniz notation. Maybe let's go back to Leibniz notation for a derivative to help us remember the difference between Newton's notation and Leibniz notation, and then we'll see Leibniz notation for an integral, which is the notation that you will almost always see. It's much more useful. When it comes to integrals. So, Leibniz notation, if I were to give you a function, let's say I tell you that 2y is equal to, I don't know, 11x minus 7. There's a function. And I tell you, and we want to calculate the derivative of the function, a very natural question could be the derivative which way? Do you want the derivative of y with respect to x or the derivative of x with respect to y? And with Leibniz notation, we can capture that notion and we can come up with it. So I need to solve this thing in terms of y if I want to calculate the derivative in terms of y. So I can rewrite this as y is equal to 11 halves x minus 7 halves. Or I can solve this thing in terms of x, and I can say that x is equal to 2 11ths y plus 7 11ths. Right? And so now, instead of just calculating the derivative one way, I can calculate either derivative you want. I can calculate the derivative of y with respect to x, which then is just going to be 11 halves. Or I can calculate the derivative of x with respect to y, which in this case would just be 2 11ths. Which we expect, right, because they're inverses of each other. And the integral derivative here and the derivative here have opposite slopes. Reciprocal slopes, not opposite, reciprocal. So that was Leibniz notation. Newton notation, we usually just have something that would have looked like this. F of x is equal to 11 halves x minus 7 halves. We don't have much of a choice in the matter. So now f prime of x is just 11 halves. So depending on how we set up our function, we're either forced to either calculate this one or this one, depending on how we set up our function. Whereas with Leibniz notation, we can go back and forth just fine. Good? So now, Newton's notation, when we're calculating an integral, the same way that it's obvious from what the function is how I take the derivative, it's also obvious from what the integral is how I take the derivative, or how I take the integral. But with Leibniz notation, we specify what we're taking the integral with respect to. So the only difference is it's the integral from a to b of some function in terms of a variable with respect to that variable. It's the only difference, and we're specifying we're taking the integral with respect to x instead of you assuming it from how the function was written, basically. Make sense?
What else could you be writing with an integral like that? So could you take it with respect to y? Is that possible?
Yes, you could. If I'm saying that y is equal to f of x, first of all, because that's what you're assuming, right?
Okay.
Then I could resolve. So let's do exactly what you're saying for a second here. So you're saying we have the integral. So I know that y is equal to, did I erase it? Put a y here. Y is equal to that thing, right? I could also solve this thing for x if I wanted. And x, what was it equal to? It was 2 11ths y plus, thank you. 7 11ths, is that what it comes out as? Or 11 7ths? 7 11ths. Whatever it is. Anyways, so now when I have my integral over here, and I want to take the integral, and let's say I have it written, well, we can plug it in whichever way you want. Do I want to integrate this thing, or do I want to integrate this thing? If I want to integrate x with respect to y, then I substitute in what I know x is in terms of y, and then integrate. So it tells me how I need to do it. If I want to integrate with respect to y, then I'm looking at this, I'm saying, I can't continue. I need to rewrite this thing in terms of y now, and here's how I do it.
Okay.
So this is the same thing as the integral of 2 11ths y plus 7 11ths with respect to y. Okay, now I have it written in terms of y, and I'm ready to integrate. And you'll memorize the rules on how to integrate things that look like this. That one's pretty straightforward. But first we need to talk about the integral as an antiderivative, which we're not ready to do yet.
Just really quick, is this upcoming test going to be similar to our derivative test, where it was proving properties of integrals rather than doing like one problems?
No, this one will be more homework problem based, having you calculate integrals by hand type stuff. I think. Anyways, now let me introduce to you another way that this notation becomes useful by doing an integral, calculating an integral by hand, same way we did last time, and seeing how it kind of leads to this notation naturally and a way to think about this notation. Because one of the ways we do think about this notation is this is the height at a function at a certain point. That's what f of x is, right? And we think about dx, we often think about that as an infinitesimally small distance. So it's the height times an infinitesimally small distance, and we're going to do that an infinite number of times. We think about an integral as an infinite sum. We often think about these as one of these. That becomes that, and then we usually represent this as f at some point x sub I times delta x. So we say that when you take a limit of something that looks like this, it turns it into that. Your deltas become d's, and then your sum becomes an integral. And I'll try to motivate that after we calculate one by hand to get us comfortable again with this calculation of an integral. So let's see. I think the one he does is x squared. Yeah, x squared. So he says we want to calculate the integral. So I'm looking for the integral from 0 to 1 of x squared, and we're doing it with respect to x. Motivate this a little bit more to help us reestablish our intuition for it. What exactly is this going to give us? If we were to draw this quadratic function from 0 to 1, so 1 squared is 1, so it's going to end here. So it's like very beginning of a parabola, right? Obviously the parabola goes off this way as well, but we just care about all over here. So we're calculating this area right here. That's what it's going to give us. With me on that? Okay. Now, this is equal to the limit as n approaches infinity of, we can take the upper or lower Darboux sum, doesn't matter, pick one. I'm going to use the upper Darboux sum, why not? So I'm going to do the upper Darboux sum, so from I equals 1 now let's figure out what our upper Darboux sum is going to be on the scene. So erase my area and let's draw some rectangles to help us get the picture. So let me draw this again. I'm going to draw it, well, we'll draw it really spaced out like this to try and help us see our rectangles better. So I'm going to divide this thing up into n pieces. Here's one. So let's draw for our picture here. I'll just divide it into 4 pieces for the picture to help us see things. And I said we're going to do the upper Darboux sum, right? So our rectangles are going to look like this. Okay, so I need to do the height of each of the rectangles, m sub I, times the width of each of the rectangles. Now we know what the width is. What is the width of each of these rectangles?
1 over n.
It's just 1 over n. How did she do that? She did b minus a divided by n. B minus a, b is 1, a is 0, because that's where we're starting. So 1 minus 0 is 1, divided by n is 1 over n. In this case, the width of each of these is just 1/4, right? But in general, if we were to divide that into n pieces, it would be 1 over n. So there's the width of each rectangle. And big M sub I is the height. Now we don't need to write big M sub I this way. We can actually calculate what it is for each interval. What is big M sub I? It's going to be f at the right-hand point. So it's going to be f at the right-hand point, maybe give ourselves some space here, and figure out what that's going to be for each rectangle. What is the right-hand point of this rectangle?
1/4.
1/4, okay, it's 1/4. But it's a regular interval, so we can also express it this way. This point is going to be a plus 1 times whatever this width is. That's our formula, right? In this case, a was 0 and b was 1. So it's going to be 1 times 1 and n was 1/4. That's how you got 1/4, right? Now, in our case, so we still have an n here. So in our case, it's just 1 times 1 over n for this one. So this point right here was 1 over n. This point over here is going to be 2 over n. And in general, it's just going to be I over n, where I is the ith interval that we're talking about. Or sorry, I plus 1. Because on this one, I is 0, so it's I plus 1. Our I, oh no, our I starts at 1. My bad. Our I starts at 1. So it is the ith interval. So here, it's just I 1 over n, which is the same thing as I over n. Here it's 2 over n, which is the same thing as I over n. Here it's 3 over n, which is the same thing as I over n. Here it's 4 over n, which is the same thing as I over n. So in general, it's just f of I over n. Sorry, I. That is the hardest part of solving these problems, is going from this to this. Once you get here, these problems become a lot easier. So let's make sure we understand how I went from this to this. We did an upper Darboux sum. That's basically what I set up here, is an upper Darboux sum, where we did the height times the width of each of those rectangles for all n of those rectangles. Okay? From here, it's real simple. So this is just equal to, we'll just write down here, this is just equal to, what is f of I over n? Maybe we'll rewrite our limit. The limit as n goes to infinity of the sum from I equals 1 to n. Okay, what is I over n?
I squared over n squared.
Oh, we didn't write what f is. Sorry, f of x. Oh, we did. It's right there. F of x is equal to x squared. So, when you plug something into f, it just squares it. So this just gives me I squared over n squared times 1 over n. Right? Now, notice n's a constant. So we can pull out this n and these n's all the way out. And now we just have the sum from I equals 1 to n of I squared, which we know how to do. So this is equal to, pull out all the n's, the limit. You can't pull out the limit, but you can pull out the sum, is what I mean by pull it out. So maybe we'll do that to make sure it's squared. 1 over n cubed times the sum from I equals 1 to n of I squared.
Isn't that just 0?
No. Obviously that area isn't 0,
Yeah,
so that should be
obviously.
screaming at you.
Yeah.
So I squared, I don't remember the formula for it off the top of my head, n times n plus 1 times 2n plus 1 over 6. So this is equal to the limit as n goes to infinity of 1 over n cubed times, this is a sum. We did this way back in chapter 1. We evaluated the sum. And the sum is n times n plus 1 times 2n plus 1 over 6. I already forgot it, and I just looked at it. N times n plus 1 times 2n plus 1 all over 6. Okay. Now we just need to expand that out. Our n's are going to cancel out. So when we take the limit, well, we'll see how this all works. Maybe no point trying to say it all. So this is equal to the limit as n goes to infinity of, let's expand out the top. So maybe I'll write this expanded out one more time in here. So we're taking the limit of this, which is equal to, let's see, we have n times 2n gives us 2n squared, but then we have that n gives us 2n cubed. And then here we have n times 1 is n times that n gives us plus n squared. Then we have plus 1 times 2n is 2n times n gives us 2n squared plus, and then 1 times n is n, all over 6n cubed. And we still need to take the limit of that. Just basic algebra, expanding that out, and then the n cubed multiplied by the 6 to put them all together in the same denominator. Good? Now I'm just going to write this as 3 separate terms. Notice that these two add together. That's why I said 3 separate terms, not 4 separate terms. So I'm going to have 2n cubed over 6n cubed, which is equal to what? 1/3. Plus, now I'm going to have 3n squared over 6n cubed, which is going to be what? 1 over 2n, right? And then here, I have n over 6n cubed, which is going to be
1 over 6n squared. And, yeah, 6n squared.
Now take the limit. What's the limit of 1/3? 1/3. What's the limit of 1 over 2n? 0. What's the limit of 1 over 6n squared? 0. There we go. The integral is 1/3. The area under that curve is 1/3. Which, if we would have drawn it right, kind of makes sense because this whole area of this box is 1, and so it takes up 1/3 of the box. My picture's lying, but a better picture would give you the truth better.
So there's an error in my thinking somewhere, and I'm thinking the product of the limits is the limit of the products.
That's true.
So you could take the limit as n approaches infinity of 1 over n cubed times the limit as n approaches infinity of the sum, right?
Yeah, but then you're going to get something that goes to 0 and something that goes to infinity. And so you're going to get 0 times infinity, and you don't know how to deal with that.
Yeah.
So keep working with it until you know how to deal with it. Just because you can get a limit in a form that you don't know how to work with doesn't mean it can't be evaluated. Every derivative you starts out by taking the limit of something divided by 0, which we can't do. So we keep reworking with the derivative until we do know how to take the limit. The answer to your question is you don't know how to take the limit of a product of infinity and 0.
Right.
So keep working with it. And if you can't get it in a form where you can solve it, then you might be trying to integrate something that's not integrable. If you can't get those infinities to somehow go away, those infinities times zeros.
Okay.
But yes, the limit of a product is a product of the limits. Any other questions?
Can we do another one?
Well, we also did the same one. We also did one last week.
Yeah, these are kind of stretching my brain.
So here's what you should do. Try doing it yourself, and then go back and watch me go through it again to make sure you can do it. And maybe redo the exact same one, and then try using a lower Darboux sum instead of an upper Darboux sum, and see if you can still do it that way. That one might throw you for a loop. Maybe don't do that. It makes the algebra kind of hairy, and if you're not comfortable working with these, then it can be hairy. So my recommendation to you is, if you're not comfortable working with sums, always use the upper Darboux sum when it's increasing and the lower Darboux sum when it's decreasing. Maybe always use the upper, actually. Because I think the hard part is working with the right hand point's easier than working with the left. Because you want to do the sum from I equals 1 to n, not the sum from I equals 0 to n minus 1. It's going to come out the exact same way, but you might be less comfortable with doing this than the way I have before. So let's do one more thing to try and motivate Leibniz notation again, and then we're done with the material. Well, we're done with what the book covers already, so, but let me try to motivate Leibniz one more way. So, and the way I'm going to do that is I'm going to come at integrals for a second, the way that you come across them in a typical calculus class, not the way that we've done here. So in general, restart conversation. I want to calculate the area under a curve. So restarting the conversation, here's A, here's B. I want to recalculate the area under this curve from A to B. And the teacher would say something to the effect of, well, one of the ways that we could approximate this is exactly like what we talked about. Divide this up into, if I were to divide it into halves, and look at the area here, pick some point between them, call this point x sub I now. We'll call this point here x sub 1, and this point here x sub 2. Pick some point on the intervals, so divide this thing in half, pick some point on the intervals, calculate the height of those points, doesn't matter. And that gives us now 2 rectangles to estimate the height of this thing, right? So here, how am I estimating the height? I'm saying that the height of this thing, not the height, sorry, the area of this thing, is the sum from I equals 1 to 2 of f of x sub I times b minus a all over 2.
That doesn't seem like a very good approximation.
It's because you're always just working with nice functions, and so it turns out it's going to be fine. So they say, look, you could have done this, and here's one approximation. Now, we could have done an even better one. We could have picked a bigger n. We could have done it when we divided this into, I don't know, force. And then this would be force. So we perfectly divide this thing into force. And now, randomly pick some points in each of those intervals, doesn't matter which points you pick, and call this one x sub 1, this one x sub 2, this one x sub 3, this one x sub 4. And then you've got this exact thing for that one's approximation, right? And then you can see now in the limit, if we do this for a very big number n, we're going to have a very good approximation. So for a very big number n, we're going to have a good approximation, so now let's write that one out. And we're just always going to find delta x is going to be b minus a over n. So we're going to put delta x here. So for big n's, this gives us a good approximation, and it gives us a perfect approximation in the limit. The limit as n goes to infinity of this thing then gives us a perfect approximation, which we call the integral, which is adding up from a to b of f of x times dx. So what do we mean by this? We mean this in a standard calculus class.
F of x times dx?
Yeah, the height times the width. This was a times over here.
So,
Delta x was the distance of one of these in the limit that approaches 0, and so they might call that an infinitesimal.
Okay.
So you have the height at some point there times the infinitesimal. You can think about it as doing it for every point on the function. For every x between a and b, you calculate its height times its width. And you add all those up. So it's like adding up infinitely many 0 areas to get an area, kind of.
Right.
So that's the way that they come at it in a typical calculus class, something like this. And so you see how Leibniz notation naturally pops out at you.
Why do we call it delta x again? Isn't delta x?
Delta x is a standard notation for a change in x. However much you're changing x in each interval. Change by that much, then by that much, and it's the same change each time.
Okay.
The same way that we thought about going back to Leibniz notation, we says the slope of a function can be approximated by delta y over delta x, our change in y over our change in x. And so when you take that in the limit, you get dy dx. So in a standard calculus class, as you take the limits of things that look like deltas, they end up with d's. And there's a lot of classes, like if you go take a probability and statistics class, you're going to start out in the discrete case where you're dealing with equations that look like this. They're going to say, okay, let's make it continuous. How do we do that? We're going to take a limit, and now we're going to be calculating probabilities with these. And you also do it in like a physics class. If you do electricity and magnetism, you're going to show you how you can start summing up some forces, and it's like this, and then now you see when we take in the limit, we get something like this. So going from this to this is something that you do quite often, which is why Leibniz notation is ubiquitous for any field using calculus. And that's it. So, have the rest of the class to get started on your homework. Oh, let me hand back Tess.